Hello. Thank you all for coming and waking up so early. My name is Tamer, or Tam for short. I work at Just Eat. Today I'll be speaking about distributed tracing in a purely functional word, and by purely functional I mean just Scala. That's all I'm speaking about. All right, so before we begin, I'll go first, introduce what is distributed tracing. Then I will give an example how to do it with the Scala. Then if you have time, there will be some live coding. All right, so distributed tracing is a part of a bigger family, bigger umbrella called observability. According to Wikipedia, observability is a measure of how well internal states of a system can be inferred from knowledge of its external outputs. Okay, what this means? It basically means that, okay, and the clicker is not working, no problem. It means this is a form of observability. When you write your first program and you write println hello world under your main, you have done observability. You have basically gave yourself a way to look at the program from its output and know what the hell it's doing. So I use this a lot. I rarely use debuggers. I use just println, print outputs, and that's it. I can reason about what's going in my system. They go to the if clause or the else clause. I can know lots of information just by looking at the output. So I will now go improve this println a little bit till we reach the galaxy mind, the last step, the distributed tracing. So let's see how we can make this println a little better. So why do I have these big arrows on the first and last line? Oh, it's not working because it works better when it's on. Yeah, now it's working. All right, so I have those big lines just to help me on my laptop to find where are my println messages are, because you might have like noisy terminal or something. You have to locate them. And this is just me on my own laptop. Nobody else is using the system. And I struggle to find my println messages. Imagine if we want to debug another problem that's running on production, and there is hundreds, thousands of users using the same server. So your printlns or your logger debugs are a bit hard to find. So yes, normally if this is in production, it will be something like that, readable message. So this is slightly better than the println. So we have logger.warn, so we can toggle the level, look only at the log messages that we expect. We have concatenated in our message some useful information, like the path of the endpoint that's failing. So yeah, this gives us some way to at least, instead of looking at 1,000 log messages, look at least 10 of those that hit the endpoint that I'm concerned about. Also, this logger will probably add for me a timestamp or something that helps me narrow down the timestamp. Just look at, look at only the parts that I care about. All right, now, this is so far would work, but I write the log message, like the time I spend writing the log message is much less than the time I spend reading and searching it. So usually the biggest problem is to find the message that you care about. So as improvement to that logger, instead of writing our log messages as just string, like English sentence, why not log a data structure, like JSON or whatever, any data structure that has key value, basically. So if we log our messages as in this style, like request path that, First, it will make my life much easier when I'm trying to look for the log messages that I care about. I can do like if this goes to like a system that has sort of SQL-like interface or any search syntax, I can say where request.path equal this. Sorry if I'm making some of you sleepy. All right, the next step, a little bit improvement to that. So I have this problem with microservices architecture. So you have this log that's printed from machine A, and machine A probably wrote or like sent another request to downstream service to be able to get your request, but maybe the failure is downstream in one of the dependencies that you care about. So we would like that the log messages from service B or whatever downstream services, I want to be able to know this log messages is related to that log message. So a common technique is to, let's go to the very first service and generate a random ID, call it correlation ID. Then every time you are doing a request to a downstream service, you propagate that correlation ID with you. So the problem with this is boilerplate. So every time, everywhere, I have to log any log message, I have to put the exact same correlation ID. Otherwise, why bother? So here comes microservice architecture. I have some messages. Yeah, so the problem is that you have to also propagate this correlation ID on the HTTP level as well. So every time you are talking to a service, you have to propagate the correlation ID with you as well. OK, boilerplate, we can work around it. We can solve it. We'll see how. But so far, there's one big problem I have with microservice architecture, is that the ordering of log messages. So all these services, they send the logs to one central place. That's where the developer probably will be looking here at the red box, the red thingy at the bottom, trying to read the logs. The problem is they're going to arrive at different times. So you're never sure which one arrived first. So we can try to order them. You can either try to order them by the arrival, so depending which one arrived first. Of course, that would probably be wrong, because maybe one service network is slower than the other. So we can depend on that. We can use the timestamps that every machine attach it to the log. But we can't also trust that, because one clock might not be synchronized correctly, might think in the future. So you will get out of order log messages, and that will probably be a little bit confusing. Final approach, the Galaxy Mind. So distributed tracing will be adding a twist to this approach. So when we receive the log in our microservice, we're going to generate a correlation ID. But we're not going to call it correlation ID. We're going to call it trace ID. So this is our first ID that we're going to generate. We're going to also generate another random ID. We'll call it span ID. So far, we're still doing the same. We're going to just propagate both IDs to the service downstream. All right? Now, this blue box is going to do something different. When it's going to log, it's going to send the same trace ID, a new span ID, and the parent span ID. So this refers to that. So now we have a sort of lineage between all the operation in our microservice. This allows me to view my operation in this sort. So I can see this is one microservice that I'm going to demo called Jokes as a Service. They are using another microservice called Jokes Provider that actually generates random jokes. And I can see which one spawned which operations. I can see the relation between them. And I also get sort of profiling for free. So this is distributed tracing, the concept. We will try now to implement that in Scala. We'll see first, we're going to write it in a boilerplate fashion, then try to reduce the boilerplate, try to work around the problem. So I'm basing my demo on a sample application that comes with HTTP4S. It's a Scala library. I only made it enterprise ready. So I added some caching around it. So in case, so the demo, the normal application goes like that. You have like a sort of a proxy. You hit your endpoint. It talks to this website, icanhas.jokes.com, returns the joke as is. So I added like a fallback. If the service is down, we're gonna go to serve like all jokes instead. I also added, of course, the distributed tracing, and we'll see how to implement it. So our application has 3 layers. HTTP layer. So this is the layer that you'd receive the request. And depending whether you are the first microservice, you might have to generate span, like generate the correlation IDs. Or if you are like downstream service, then you just have to receive this ID from the header and just obey the information that you have received. Then there is the middle layer in your application. Could be 1, 2, many. All these layers, they all care about is just propagating the span. You just have to take it from one side, deliver it to the other side. The last layer of your application, the layer that does I/O, does interact with other microservices, there is when we actually need to read the span in order to put it in the headers of the requests we are making to other services. So we'll start first with the middle box. We're going to implement the one that just passes the span. So at the bottom, we have this box in the middle, just get joke. What it does is first tries to get new joke called the actual website. If it doesn't work, then fall back to getting an old joke. So far, no tracing. So the manual way, the mechanic way that just works, but lots of writing, is to go to every single function in your code base and add one more parameter. Just do the span manually. It works in a small, if you have a small code base. But after time, you'll find it a bit tedious to keep doing it yourself. So we'll use from Scala a library called cats that has something called Clysely that we are going to reinvent in this slide step by step. So first, I'm trying to hide span. I don't want to see it in my code base. So I will move it from being a parameter. I will move it to the other side, to the return type. So instead of having a function that returns my operation directly, I/O. Oh, by the way, I forgot to say what's I/O. So if you come from Haskell, you probably know what I/O is. If you don't know it, I could say just consider it something like future or promise. I know I have offended people by saying it's like future, but just for the purpose of this talk, yeah, we don't really care about the difference. All right. So instead of accepting span as a parameter, I'm just returning a function that's still waiting for the span. So we have, we can now introduce type alias to even furthermore hide the word span and just use it and hide the word span. We only now still have span here down at getJoke. because we're still doing the propagation manually. I would like to get rid of that. I wish if I can go back to the initial implementation and just write get joke or else get all joke and just let the computer figure it out. Thanks to cats and cats effect, we already have this construct that's called Kleisli. So Kleisli is basically a wrapper around my function. So if you open, I don't have the source code now, but if you open how Kleisli is defined, it's just a class that is wrapping the function from span to IO of A. But the good thing about Kleisli, that's also defined for us some implicit instances, some type class instances that we need to do basically everything we do with I/O. We can do it with Kleisli of I/O as well. So this could now compiles. I could say this operation or else that operation. And the monad instance or the sync instance of Kleisli is taking care of just passing the span down to the next level. All right, so this is pretty much the middle layer, jokes as a service. Now let's see how to implement the last layer. When we actually need, when we're writing the client, when we actually need to read the span to write it in the headers of the HTTP request. So the easiest way to do it with Kleisli, just remember, Kleisli is a function, it's wrapping a function. So we can almost write that. We can just say it's basically, the output is going to be a function from span, and the body of that function is something that returns I/O. Just the only difference, we have to wrap it in Kleisli because just Kleisli is a wrapper. That's about it. That's the easiest way to do it with Kleisli. So we have now solved the last layer. Now we go back to the very first layer, HTTP server. We want to create the span. So here we have, this is HTTP4S syntax. We are defining our roots. So this block, as you see on the top, of the HTTP routes of I/O. So it's expecting us to return something, I/O of something. So it's expecting I/O. But we have joke service that's returning traced I/O. Still, this is waiting for a span. So waiting for me to pass the span. So dot run, this is how you get from Kleisli to the function that is, to call the function that is underlying it and get the I/O. So we just need to create the span out of thin air. And this is the perfect place for it because we have the request. We can just look at the headers. Are we, like, is there in the headers the necessary information? Good. Create the span out of it. Nothing, generate random one and make a span out of thin air. The last thing I want to do after our operation runs, I would like to log the span, log the termination. Does it succeed? Does it fail? So cat's effect gives me this function, guarantee, which is similar to try finally. So this block is guaranteed to be called even if get jokes failed. All right, so now we are moving, just before we move to the demo, I'll just show you, you know what, I'll just go to the demo first, then I'll go back to the slides. So this is the same thing, but it's written using a library that I'm still developing called pure tracing.
I'm sorry, could you increase the font size a bit?
Right.
Perfect.
Properly. Just for a second, I want to cancel the turn on mirroring because I can't see what I'm presenting. Yeah, that's much better. Right, so the slides were a little bit simplified version of what you write. So this code is written in tagless final style. So instead of writing that my function returns IO directly, I abstract over it. I say it's whatever f is. Then I put some implicit instances or type classes to say, oh, my f has to have sync, or it has to have this functionality. So also we have this pure tracing type class instance, which is basically works if you have Kleisli, if you're using Cat's effect, or if you're using Monix or ZIO, that you have some functionality like task local or fiber local. So for now, let's focus on Cat's effect. So I have this tracing instance, which gives me the functionality I need. So I just give it the operation name. It logs before, logs after, calculates the latency. It basically piggybacks on a Java library, but yeah, you get the functionality you expect. So let's see this running. So on the right-hand side, I have my, this was the first box, the one that has the HTTP4S code. This one is supposed to be the actual website, but I'm replacing it with something I can control. So consider the left one is the provider, the one that generates the jokes. So I'm going to hit it. Oh, it's Wi-Fi. Because the one on the left actually talks to the server. Okay, that's actually a good thing. So the one failed. I was not expecting it to fail. I was expecting it to work. But because we had or less or else, so we had the other branch kicked in, and we got an old joke. Not interesting joke, but at least we got a response. So let's see the logging. What do we have? So 11, yeah, that's the one. Ooh, that's an interesting one. So I have the logs that says HTTP4S. Well, let me increase. Okay. So first thing I hit the HTTP4S, then it calls getJoke, which tries to get the proxy, but probably the proxy fails, so we fall back to get old span. So I see here what happened, and I see as well, sure, on this zoom level, things are not, yeah. All right, let me fall back to another old one because the timing is not showing properly here. So let me get to last 6 hours. I promise it worked at home. Yeah, so I just wanted to show the time difference. So jokes provider, when it replied, so you see that how many time, like the amount of time you spent on actual network and how much time you spent on the actual service. So you get all the profiling in production already for you, just if you use this library. All right, do we have time for questions? Yes, okay.
Have you evaluated AWS X-ray for this?
The question is, did I evaluate X-ray for that? So do you mean the library, the Java library, or the backend X-ray?
Both, but in particular getting it to work with, HTTP4 and the rest of it.
All right, okay. First, let me talk about the Java, the actual library. So you still have to enrich your program to do the propagation yourself, because the Java one, if you are using Cat's effect or using ZIO, it depends on thread local. So it doesn't work with the modern like fiber-based effect systems. You can use it with Scala futures. There's some tools that does monkey patching, modifies the code of future to add the propagation for you. You can use that. I guess it's not free. One of them is open source. One of them is not free. You have to pay for it. So if you're using CATS or using ZIO, you still have to use this library. You have to use Clydesdale yourself to propagate stuff. Using the back end, I think with my library piggybacks on two other Java libraries. One's called Open Tracing. One is called Open Census, I guess. Don't remember the name. If you use that one, it integrates with X-Ray. So yes, you can view your output in X-Ray via two adapters.
And is it a good idea to do this, or is it better to use something else?
It depends. I mean, like if you're on AWS and you don't want to install Jaeger yourself, and because there is also database behind it, so there's some infrastructure. Yeah, I mean, it works as well. Oh yeah, let me go back to the slides. The code, just asking the code published. So the one at the top, this is the library that's targeting CATS effect. The second link is pretty much the same thing, but just focused on ZIO, works only for ZIO. The last one is basically the code that I have just shown you. I'm trying to get both of them in one library. But I'm still abstracting over CATS and ZIO at the same time. Is not particularly easy because the way they do like bracket, like error handling, like bracket, or want to make sure to call code, like basically guarantee, the method guarantee I've shown you, is a bit different between those two libraries. So I'm still trying to figure it out. Questions?
I mean, since it's quite a pure approach, it might not matter that much, but have you done any like a performance benchmark regarding, like, say, garage collection, pressure, and so on?
No, so he's still early. No, he didn't do anything.
To this point, we had a Liberty wrapper for precisely this purpose, for tracing, and it slows down our production load like 4%. So it's not much.
Is this slowness because of Clydesdale itself?
Yes.
All right.
So when we compare without tracing.
All right. So the implementation that's using ZIO is not using Clydesdale. It's using fiber local from ZIO. So maybe have a look.
Faster.
Yeah.
And also we tried to use task local from Monix, but it doesn't work too well.
Yeah, I've seen some. Yeah, there is some problems with task local and fiber local, and also it becomes some hairy when you are forking if you're doing things in parallel. But I do have some guidelines that I'm planning to publish later.
Okay, so this looks really great for a greenfield project that you're starting from scratch, but where distributed tracing is most useful is when you have a large system.
Yeah.
Do you have any advice for trying to put distributed tracing into a large existing system where you can't just change all the code to thread or you just
Yeah.
That is a great question, but I'm afraid I have to interrupt. We're out of time. So
All right.
maybe you can take that one off. Take that one off.
All right. Okay.
Thank you, Tam.
Okay. Thank you.